In this last section of Chapter 6, Section 4, before we have our test, we're going to look at irrational numbers and decimal representation. Now, we did define earlier what a rational number was. You may recall it's a fraction in decimal form that terminates or repeats. But there are some numbers on the number line that in their decimal form do not terminate, do not have a repeating pattern. So these are the irrational numbers. And the definition is right there. So let's go on and look at some examples. Some we had mentioned earlier was the square root of 2. And when you see that you have a radical in a particular term, this is considered irrational because of the presence of that radical. Some other famous ones, of course, is pi, which we use in the circumference of the circle and area of a circle and volume of a circle. And another one that we had mentioned earlier, E, the letter E, it's approximate to this value, and that was named after Euler, where we did some of his diagrams in a previous lesson. And here we look at the irrationality of the square root of 2 and proof by contradiction. Now, this was something we had earlier, but didn't go into it that much. So let's take a look at these figures before we go on. Here, this is a right triangle. And we said if we square the short leg, added to the square of the long leg, it equals the square of the hypotenuse. And we also mentioned that if we had a isosceles right triangle where two sides were equal in length, let's say 1 and 1, then we showed you the work that the hypotenuse was the square root of 2. We're not going to go into detail here, except to mention this is proof by contradiction. And I thought a little bit of Latin here was interesting. This method is also called reductio ad absurdum, reduced to the absurd. And it ties in with what we said was whether a fraction in an earlier lesson would have the prime number 2 or 5, the prime number 5, in the denominator when it was simplified. If that were the case, recall, those numbers were rational numbers and had a decimal that terminated or repeated, qualifying it for a rational number. These irrational numbers, you cannot express them as a fraction. All right, let's go on. Again, since we had not done this in an earlier, I believe it was chapter 1, we're not going to have you go through this now, but I thought this was interesting. I remember doing this in one of my high school geometry classes. So here we have a right triangle, isosceles right triangle, and the side of this is 1 and 1, and we proved that this was the square root of 2. Well, if we keep these sides as a 1, we now have one side as 1, the other short leg Well, this is the shortest of 1. This is the little longer leg. But the hypotenuse now is this one, which is the square root of 3. And again, if we put that in a Pythagorean theorem, the sides, which were the hypotenuse, become the square root of 4, square root of 5, square root of 6. Now, notice when we got to the square root of 4, square root of 4 is rational. And again, when we get to the square root of 9, the square root of 9 is rational. That's 3. Okay, and then we continue, and it would go on for a while. A very interesting thing. And we find in nature some of the shellfish that have this particular pattern. And it's interesting, they never studied geometry, but yet that's how they developed. Thought that was interesting. Now, we often in our calculations deal with rational numbers, but every once in a while we deal with irrational numbers. Remember that under the radical sign, they have to be positive. We have not defined negative radical signed numbers. So, looking at these are not perfect squares, so therefore they're considered irrational. But the square root of 4, as I just mentioned, is a perfect square, so therefore when you take the square root of it, you end up with 2. Remember, the radical sign is an operational sign. It says take this of that number. And this is a perfect square, and so is this. Now, when we put this into our calculators, and if it is irrational, it'll give you a string of decimal places. And often we're asked to round to the nearest thousands or 4 digits or whatever they ask us to do. So let's look at an example here where using your calculator you're asked to do these. And there's the square root of 2. We usually think of it as 1.414. Square root of 6, I don't know that anymore. And the square root of 1949. That was when I was in the 7th grade. And the wavy lines indicate it's an approximation since it's not an exact answer. Now, how do you put that in a calculator, by the way? Often in a calculator there is a radical sign. And let's just go over that for a moment. This is called the radical sign. And what we put under the radical sign is called the radicand. And sometimes you'll see a number here. If there is no number, then we assume it's a 2. So we'll be working with this, and these are called radicals under the radical sign, the radicand. And this is the index number. Here we're asked to apply a formula for pipe flow. Well, they're giving you the number n of the smaller pipe of a diameter d that are necessary to supply the same total flow as one larger pipe of a diameter capital D. So there is the formula, and they're giving us various values to put in there, which we see listed below. And what you would do first is to figure out what's going on here. So let's pause and review that. So as we put the dimensions of our pipe in there, this is division within a grouping symbol. So we do this first. And we said we did division by converting division to multiplication. and taking the second item and flipping it. So it was 1/2, now becomes 2 over 1. And now the 2's cancel out. So this gives us a 3 that we're going to raise to the 5th power. Put that in your calculator and get 243, and then take the square root of that. And notice, while this is an exact answer, this will be an approximation. And we're rounding it to 2 decimal places. Now, some of the things that we're going to do with radicals, for instance, we could take the square root of 4 and get 2, and the square root of 9 and get 3, and 2 times 3 is 6. Now, what they're indicating here, we could have put both of the above radicals under the same radical sign. This would give us 4 times 9 is 36, and the square root of 36 is 6. This gives us the property, the rule of what is listed here, that the square root of A times the square root of B can all be put under a common radical sign. Okay? Now we do want to simplify radicals, and there is a protocol for that that we'll be going over. Now there is again a definition, so to speak, of conditions for a simplified square root radical. To be in its simplified form, first, the number under the radical sign, that is the radicand, has no factors that are a perfect square. And there are no fractions in the radicand. And the denominator contains no radicals. So we'll be giving examples of this. Here is a listing. Now we do similar topics to this in our Math 105M program, and here's how I would explain it. We want to simplify this radical. Well, I tell the students, if we are going to try to simplify, put 2 sets of radical signs. Now we're looking for 27 factors of 27. Is there a perfect square factor of 27? And we want the largest one. And if you think about it for a while, you might say, yes, 9. So under one radical sign, you put the 9, and then what's left, you put under the other. So what is the square root of 9? 3, and we just write the square root of 3. Now if you could remember that the square root of 27 is always 3, the square root of 3 simplified. Now if we put this in our calculator or this in our calculator, we get the same approximation. Now here they're showing if we have a radical in the numerator and a radical in the denominator, we could put them under the same radical sign. And if we could simplify this, we could do that. So let's look at some example. Now, for example A, remember we could separate that and say radical 25, radical 9, and this is just going to be 5 over 3. And in example B, we could say radical 3, radical 4. Here, this isn't a perfect square, so that would be radical 3. Now the square root of 4 is 2. Notice this meets our criteria for simplifying, because where there was a radical in the denominator before, now there isn't one. All right, let's look at this one. We have the square root of 1 over the square root of 2. Now, the square root of 1 is 1, but there is no perfect square factor of 2. 2 is prime. So we need a technique to deal with this, to get rid of the radical in the denominator. And the most common way is to multiply this fraction by 1 to make it an equivalent fraction. But, so we end up with the square root of 2 not being a radical anymore. So the form of 1 that we choose is the square root of 2 over the square root of 2. Now, this is the most common use of this, where, again, in blue is a 1 that we're now going to multiply numerator and denominator by. In our numerator, this becomes 1 times the square root of 2, or just plain square root of 2. Remember, there's a 1 in front of everything. We just don't write it. And now square root of 2 is square root of 2 is the square root of 4, which is 2. Now, we describe this as rationalizing the denominator. They're not giving you those words here, but that's what we call that. When you have a radical in the denominator, that's irrational. By multiplying it by something, we make it a rational number. So now this has been simplified. And here we see the word. We've gone from an irrational number to a rational number. We have rationalized that denominator. And we see that illustrated on the next page. Remember, in this form, it is not simplified, but in this form, it is. Now, we can work with radicals, add them, subtract them, multiply them, but when we are adding or subtracting radicals, we can only do that to like term radicals. That is, when what is under the radical sign is the same. These are like radicals. So we're going to see this illustrated in example 5. All right, let's look at this. Here, this radical is exactly the same as this radical. So you have 3 of these and 4 of these, and generally we just add the coefficient or the term that's outside, or the part of the term that's outside the radical. So this would give us 7, the square root of 6. Now here they're showing you, as you factor out the common square root of 6, and you just add what is outside. Now here you might say the radicals don't look alike, so we have to play with them a little bit, and let's show you what we do here. We're going to use 2 sets of radicals to simplify this term, and then later 2 sets of radicals to simplify this term. And remember, there's a subtraction sign between them. Now, is there a perfect square factor of 18? And you might say, yes, 9. And then 2. 9 times 2 is 18. So we'll leave it like that for now. How about our 32? Is there a perfect square factor of 32? And again, if you divide that by 2, you get 16, which is a perfect square, and what's left over is 2. You can see where we're going with this. What is the square root of 9? 3. The square root of 2, that's left over, minus the square root of 16 is 4. The square root of 2. Now we have like radicals. So again, we could factor that out as they're doing it. 3 minus 4, the square root of 2. So this ends up being a negative 1, the square root of 2. And generally we don't write the 1. It'll just be a negative square root of 2. The work is in our book to support what we've just done here. All right, looking at some of the other radicals here. Continuing our study of numbers, we're going to take a look at the irrational numbers, pi. And this one this is thickened a little bit up here. This is thickened around there too, I guess. This is a Greek letter phi, P-H-I. So this is phi, and this is pi. So they sound very much alike, pi and phi. And then this is just E. And that was the EU that we had, that Euler's that we had talked about before. Okay, and there it is right there. Euler, we're a famous mathematician, and it was honored by giving this value, letter E. All right, and we use this as a natural exponential and in natural logarithm functions. We'll be reviewing that a little later. And where it sounds like pi, I don't believe it has an E there. So there is pi, and this is an evaluation of it. This would be phi, which is this Greek symbol, which is this approximation, and this is E, which is this approximation. Now, if I were to tell you memorize these, I would have a trouble with that myself. But again, you can use your notes. And here's a closer approximation. Yes, if you're a savant, maybe you can remember that. And here are some examples of sites where you can find more about them. Okay, computing the digits of pi using an infinite series. Here we see the work. Again, I'm not sure where we're going to use this or what we're going to do with it, except to know this is the pi using the infinite series, and it's approximated a little higher than our usual approximation of pi, 1.4, 3.14, etc. This is 3.189. Again, it's available as a reference in our textbook and hopefully in your notes. All right, going on to this next one, which is phi, and there's the spelling of it right there. And this is referred to as the golden ratio. So here we have a square, and then we have this other part where we're adding a width to it. And this proportionality that they're showing here is used by the Greeks, as I recall from my ancient history classes and art classes. That is a beautiful golden ratio. And it's this, basically. And we said the approximation of this is this. Now, most rectangular photographs, you recall, are this, and paintings are this. This is the golden ratio. And some more references that if you'd like to do something, again, we're not doing term papers in this course. The computing the digits of phi using the Fibonacci sequence. The first 12 terms are this, and it gives us this. Again, I'm not sure how much in detail we're going to have to remember or use this. You'll see what they're going to ask you in your practice and homework in QuizMes, and we'll let you know what the test will contain from this. Okay, there's the irrational number E now. Again, it's figured out. I've seen proofs of this, how they were able to generate this number, and we're not interested in that either. Just to know that it's approximately, if we round it to the first 4 digits, so 1, 2, 3, 4, we're going to drop the 8 and add a 3 to the 2. Okay. And this is the infinite series that converges to this up here. Well, we have some pretty heavy things here. Okay. Again, nicely, our calculators have this value of E built into it. And to wind up today's lesson, we'll work on some of these exercises in class as part of our study of the text.